Now, I did not understand Herbert's wonderful introduction, so I'm not sure if he's mentioned this, but we will not have simultaneous translation in this room. I will try to speak slowly, and I'll be showing you a lot of things in JMP. If you have questions, please raise your hand. Herbert can come and help if there's anything that he needs to translate, and also we can go at whatever pace makes sense for everybody. So I'm very glad that you're here. I think you're here to learn about the profiler, which is an amazing tool in JMP. How many of you are using the profiler, have used the profiler? So there are many people in this room who've never used the profiler. That's very exciting, and I'm glad to see that because I think I can show you some very interesting things and great possibilities with this tool in JMP. The profiler is in several different places, so I'll show you several parts of JMP, and the profiler will show up in several different places. There's slightly different features depending on the context, and we'll see a lot of that in this today. So we're going to talk about what the profiler is, and then we're going to look at problems that you might have that the profiler can solve and how to use the profiler to solve those problems. We will specifically look at things where you want to evaluate a formula, for example. The profiler is a great solution for that. We'll look at things where you want to visualize a model. The profiler is a great tool for that. We'll look at things where you want to interpret your statistical model. The profiler is a great tool for that. And then we'll talk about optimization. So if you've got some kind of a complicated surface and you want to find the optimum, either you're maximizing or you're minimizing, maybe you have multiple responses, it can get very complex, and the profiler is a great tool for this. One scenario that will carry through the entire hour is this scenario about tire rubber production. So this data set is called Tire Tread, and it's a sample data set that's built into JMP. So if you have your computer and if you have JMP on your computer, you'll be able to follow along with me with all of these examples. You can also download, I will use a JMP journal that looks like this and has all of the data sets linked in it. If you want to find this JMP journal right now and download it, you can go to jmp.com, jmp.com/discovery workshops. Let me see if I can, not sure where I can write this. Jump.com/discovery workshops. And there you can download a document that has all the steps I will go over today. It will show you the example. It will show you screenshots. It's everything we'll cover today. And you can also download this journal if you want to follow along with me. So I'll give just another moment for anyone who's going to jump.com/discovery workshops to download those materials. And I'll remind you at the end as well. So this particular, yeah, yes.
혹시 다운을 적는데 어려움 있으신 분 저한테 손 한번 들어주시면 도와드리겠습니다.
So this data set that we're going to use for a lot of things in this hour is called Tire Tread. That's the name of the data table. And what we've got in this data set is 3 factors: the silica, the silane, and the sulfur. So we're going to, this data came from a designed experiment where we were varying the amount of silica, the amount of silane, and the amount of sulfur. And we're looking at the resulting tire rubber to see how it ranks on our ratings of abrasion, modulus, elongation, and hardness. So we have 3 factors of interest. We're treating them as continuous factors, and we have 4 responses of interest. So we will use this for several things in this hour to show many different things about the profiler. So first of all, what does a profiler look like in JMP? The profiler is a visual way to look at an equation. That equation is usually coming from your statistical model. So if you use fit model in JMP, it puts together an equation to connect your factors and your responses. So in this case, what we're looking at is a formula that is behind the scenes for the profiler. And that formula is saying your response, in this case abrasion, equals some kind of slope, some number, or intercept, plus a slope times your first factor plus the slope times your second factor, et cetera. And then in this particular model that I've built, I also have two-way interactions. So that JMP is fitting that model. You're not bringing it the equation. JMP is fitting that model and then showing you that model in the prediction profiler. You can also come with your own equation and use the profiler in JMP. So I'll show you some of that later. But most of the usage of the profiler is because JMP has fit this and given you the equation, and now it's showing you what that looks like visually. So it needs a formula in the background. It's going to give you one row of these panels for each of your responses. Here I only have one response I'm showing you. And it's going to give you one column of a panel for each of your predictor variables or each of your factors. When you're using the profiler in JMP, there are many ways to interact with it. JMP is a very interactive software. Our goal is to help you feel like you're really in there with the data, with the model clicking around. One thing you can do is to click where those little red crosshairs are on the plot. You can click and drag to move that around. You can also just click where the value is and type a new number. And you can also use menu options to adjust the place in the profiler that you're looking. What those crosshairs are telling you is the X, so silica at this spot, silica is 1.2. At this spot, that corresponds to silane of 50. And at this spot, it corresponds to sulfur of 2.3. When you've got that factor setting, then this is what your predicted abrasion is. So it's showing you visually one factor times by the response at a time, but they're all connected to each other. So our prediction for abrasion is 133.1. There is also, so here's how we're getting that. Here was that equation. So that 133.1 is coming from the pieces of this equation where we plug in the values that we're putting that factor setting. So that's what we're seeing here. There is also an interval shown on the plot. That's a confidence interval for the mean. So that tells us that at this particular factor setting, we expect abrasion to be 133.1 with a 95% confidence interval of 129 to 136. There is a difference between a confidence interval and a prediction interval. The confidence interval is if I did this experiment with all these experimental runs over and over and over again, 95 out of 100 of the times I redo the experiment, I will get a prediction for this factor setting in that range. But you might want a prediction interval. That means if I do this factor setting one more time, where do I expect the new value to fall? So you can also ask JMP for a prediction interval, and you can see it's wider. So this is very easy. We'll do all of these things in a moment in a demo. All right, so a little bit more about what's behind the scenes, what's happening. What are the black lines that are showing us this formula? They're a cross-section of this multi-dimensional surface. So here we have 3 x's and 1 y. So we have a 4-dimensional surface. That's hard to show you. So what if I simplify it and I make it 2 x's and 1 y? Now it's a 3-dimensional surface. I can see a 3-dimensional surface more easily. So this line, this is the trace or the profile when I fix silane at 50. So here silane is 50. What is the trace at silane equals 50 if I sliced that 3-dimensional space? And likewise, when I hold silica at 1.2, what does the trace for silane look like? So that's what we're seeing. We're seeing one slice of a many-dimensional surface. Okay, so you know a little bit about what the profiler is. Now let's start using it and doing cool things with it. So one thing we might want to do, let's say I'm an engineer and I want to visualize the expected response based on my factors, and I want to try different factor scenarios, different settings of my factors, and visually understand what my model is telling me is going to happen. This is the exact scenario for the profiler. That tool is going to help us explore that space. So I'm going to show this to you in a small video, and then we'll go back into the software and we'll all do it together. But I think this way we can stay on track, and then we can practice. So here we have the 4 responses for this example and the 3 factors, and I'm just clicking and dragging in order to explore that space. So you can see everything's connected. I can see how all 4 responses update as I change what my factor settings are. So I can do this by clicking and dragging. I can also do this by clicking here and entering the value I want. But it's a really great tool for just understanding what are the predictions. What does that space look like? If I want to know at this factor setting, at silica equals 0.554, silane equals 59.25, and sulfur equals 1.68, at this setting, what is the predicted value of elongation? Very easy for me to use the profiler to answer that question. What is a 95% confidence interval on that? And if I wanted the prediction interval, also very easy for me to request that from JMP. Okay, so what if I want that prediction interval? What do I do? I'm just going to use this little red triangle to find more options. So this is how JMP works. It's a progressive interface. You do something in JMP, and the red triangle gives you new options that make sense in that context. So here we go. If I click that red triangle and choose prediction intervals, there we go. So very easy to add on some extra features. I can, again, click and choose new factor settings. So for silica equals 1, silane equals 60, sulfur equals 2. What is the predicted value of abrasion? It's 133 point whatever. What's the 95% confidence interval? What's the 95% prediction interval? What if we want it to look a little different than the defaults? JMP has made some choices. What if I want to make different choices? So if I want to make this look a little bit different, there are options under a term called appearance. So way at the bottom, appearance gives you some things you can easily change. So here I've put extra space between the panels. I can reorder the X variables. And here, even though I have 4 responses, I'm going to hide a couple of them and only show 2 of them. So there's many things we can do from that red triangle. Once we get the profiler, there's a lot of ways we can customize things. Okay, here's a weird one. This is a little bit different than what we've looked at, and I'll give you a different example for this one. It might be the case that you have built a model on factors, like maybe my model uses Z1 and Z2 as my factors. But Z1 and Z2 are actually functions of other factors. This happens a lot if you do transformations of factors. You might fit the model on the transformed version, but really want to look at it in terms of the original. This is very easy to do in JMP, so let's do that. We're going to use a profiler in a different location for this example. Instead of fitting a model and finding it there, we're going to go to the graph menu, choose that profiler, and then we're going to have an option called expand intermediate formulas. So this guy looks like this. This is what my data table is. And you can see I'm clicking on the data table, these plus signs that show me the formulas. So yield was in terms of 3 variables, but 2 of those variables are in terms of another variable, reaction temperature. So if I go to the profiler and I fit yield, first it shows me that in terms of the 3 variables, K1, K2, and reaction time. That's what I actually fit it to, but I don't want it in terms of this K1 and K2. I want it back in terms of the reaction temperature. So these are the 2 ways I could look at the profiler. One in terms of the variables I actually fit, one in terms of the original variables that they were built off of. So the JMP profiler can do many, many things to help make it easier for you to visualize what's actually happening with your data. Okay, what if we use JMP? We use the DOE platform, we design an experiment, and that experiment includes a constraint. So a constraint might be disallowed combinations of factors. Maybe I don't want the low temperature and the low time. I only want medium and high temperature and crossed with low, medium, and high time. So there might be some combinations of factors I don't want to include in my experiment, or I could have a linear combination. Maybe there's a part of the design space that I don't want to use. So if we design something in JMP and it has a constraint, that constraint will carry through all the way to the profiler. You can also add a constraint in the profiler, but it's gonna make a lot more sense if we've designed it this way. We already have the constraint in the design, so I'm gonna show you this way. So this is gonna be another red triangle option from the prediction profiler. This particular example, we designed using the DOE platform, and when we did that, that's when we set up this constraint. When the DOE platform made this design, it generated all these scripts for us, including this one that reminds us of the constraint that we've already set up. Now that we're in the profiler, you can see that there's regions that nothing shows up. That's because it's a constrained part of the region. You can see that I can still keep trying to drag, but when I drag one of these guys, so this is me showing you how to change that constraint if you wanted to make it looser or tighter. So now as I drag, you'll notice that it moves the crosshairs on this one also. Usually in the JMP profiler, you're only moving one thing at a time, but because of the constraint, it says you're not gonna be able to move in this direction, so I'll move this other one at the same time. So the constraints also show up in the profiler. Okay, so this is our first of 3 demos. I'm gonna pause here, and if you have JMP on your laptop and you can open this up, we're gonna do this together, and we're gonna look at many of those things that I just showed you and make sure that you know how to do them. That is not what I wanted to do.
여기까지 했을 때 질문 있으신 분 있으신가요?
Okay, so I'm gonna open that tire tread data. If you did download that JMP journal, you should have this open, and you can click on this tire tread example. If you need help getting there, just raise your hand and Herbert can help. And so this was our example that we looked at for most of this. We've got silica, silane, and sulfur as our, not what I'm trying to do, as our predictor variables, our factors, and we've got abrasion, modulus, elongation, and hardness as our responses. So I'm gonna use one of these scripts on the side to fit a model. Let's just start with abrasion. So I'll use this abrasion quadratic model. So I see that abrasion in this profiler. I see silica, silane, and sulfur. I also see a row for something called desirability here, and then on the other side. We're gonna ignore that right now. That's gonna help us when we're optimizing this function, but right now, we're not as interested in it. So I might wanna turn it off. If I go to the red triangle by prediction profiler and go down to appearance, another thing I didn't show you yet is that I can hide desirability row. So if I turn that off, that's a little bit simpler. Other things we looked at under this red triangle are the prediction interval. This is how I turn on prediction intervals. If I wanted to adjust these settings, I can click right here and type, for example, 152.5. Maybe that's the setting I want to explore. So now I see the predicted value, the confidence interval, and the prediction interval. Also from the appearance, I can add that graph spacing in between the panels. That's one of the things I can easily turn on. So graph spacing, if I add 5 pixels between, it separates the panels a little bit. These are just things I can do to customize this. There's actually many more things we can do to customize the look, but some of these things are just from the red triangle, very easy to do. Another thing that we'll talk about more that I didn't show you yet is you can turn on the data points as well. I think this is a wonderful feature for helping to understand how the data support that model. Why did JMP fit this model? It's because it's the curve that fits based on the terms we asked it to fit. It's the curve that's gonna fit into the data the best possible. So if I move myself around this space, you can see some of these dots are very dark and some are faded, like they're far away. JMP is showing you the data points that are close to where you're looking in the space as dark points, and the other data fades as light points. So you can get a better sense about how well the data support the model that you're looking at. Like what's going on with this data point up here. It's very faint. I'm near it on the silane space, but it must be very different from where I am in silica or sulfur, so I could try to find how do I get closer to that point. So if I move silica closer, now this is getting darker, so I'm getting closer to the space where this guy is. Now another way we can look at the data and the model is with a 3D scatter plot. So there's also graph and scatter plot, 3D, scatter plot 3D is another way for us to explore what that model looks like. We'll just do that really quickly. So if I used, let's do this with just the factor space, the silica, silane, and sulfur. If I put those into Y and say okay. And one thing I always change every time I use a 3D scatter plot is the size of the dots. So I'll right click and go to settings and I'll make the marker size larger. But now I can understand the factor space better. This was a designed experiment, which is why the points are all separated so in such a formal way from each other. So there are other tools for visualizing that aspect of it, but what's great about adding the data points on the profiler is that you see the model with the data, and you can understand if there's parts of that model that aren't as supported by the data. Are there regions of your model that are not fitting the data as well? That's easy to explore when you add the data points. Okay, any questions? This is the end of our first demo. We're going to go into interpreting model things after this, but is there anything else from this section, anything that I showed that you want to see?
질문 있으신 분? 아, 이거 또 한번 보여주세요. 너무 빨랐어요. 이런 거 없나요?
혹시 한국판에서는 어피어런스가 어떤 부분이
Okay. So this next section is going to be some tools in the profiler to help you interpret your model. So the profiler is helping you see what is the statistical model that was fit to these data? What does it look like? How does it fit with your data? So how do we use the profiler to help us interpret what's happening in the model? Well, when you fit a model, you're usually going to get something like this effect summary. This effect summary is giving us p-values associated with the model terms that we asked for in this model. So we can see that silane, silica, and sulfur, the main effects, are very statistically significant. They're very tiny p-values. What that tells us is that the slopes of these lines are not flat. They're either statistically significantly positive or statistically significantly negative, but they are not just flat. So that's what the top three tell us. Each one of those is a main effect, and the way that's being calculated is for silane, it's saying averaged over the other two, is there a positive or negative slope versus a zero? Which means it might be the case that the slope for silica is actually flat in another region of silane or sulfur, not just at the average. Interactions help us understand that. Interactions help us understand, does the slope of silica change depending on where I am in silane? If I move that red dotted line in silane, will I see that silica changes slope? If the answer is yes, then it's a statistically significant interaction. So I can already see without clicking around, I already know the silane by sulfur interaction is very highly statistically significant. The silica by sulfur is also statistically significant, and silica by silane is borderline. So I already know I will see those slopes change as I click around in the other variables. So here's the silane by sulfur, significant interaction, and here I can see it. So I'm moving myself in silane. I'm starting right at the middle, and then I'm going to move in silane and watch silica move. So I move down in silane, and it starts changing the slope of silica. It also starts changing, well, I guess sulfur is the one I'm highlighting here, so it changes the slope in sulfur even more dramatically because that's the stronger p-value. So when I've moved across the range of silane, so I have a low value of silane and then I have a high value of silane, the slope of sulfur is quite different. One of them is basically 0, and the other one is pretty steep. That is an interaction effect. So between looking at the p-values and playing with the profiler, you can understand a lot more what's happening with your interaction effects. But there are other newer tools in JMP as well in the profiler to help you explore those interactions. Yes?
일단 기본적으로 한국말 쓰고 계시는 분들은 메뉴의 위치가 바뀌진 않아요. 그러니까 메뉴의 순서는 동일합니다. 그래서 영어로 되어 있긴 하지만 순서가 같으니까 그거를 유의하시고 보시면 되고요. 지금 이제 해석 관련해서 얘기를 했는데 혹시 해석 관련해서 질문 있으신가요? 난 이거 좀 설명 좀 해주시면 좋겠습니다. 다들 아시나요? 아주 훌륭하신 분들. 아, 좋습니다. 네. Sorry, I just wanted to like, yeah.
I trust you. I don't understand, but I trust you. If you haven't met Herbert, Herbert is so good at what he does. So if you have any questions, you can ask now and we can both help you, and you can also find us later on and we can help you with wherever you're looking. So in the prediction profiler, there is now a tool to turn on these little interaction lines. So I still see the main profiler line and confidence band, but I also see these light lines. They're helping me understand how extreme that line might be depending on where I click in another variable. They're only capturing two-way interactions. So it might be the case that if I move silane really far and sulfur really far, that there's actually another line that's not captured here that I haven't seen yet that appears. They're two-factor at a time interactions. But this gives us more of a sense of what's happening with these interactions. So we'll look at that feature in a moment. So if I want to visualize the impact of two-factor interactions, how does the profile of one factor change, the steepness of it as I change the levels of another factor? This is called overlaid interactions. And another thing I can do is turn on those data points, again, to help understand how supported is the model in that region that I'm looking. So we'll do that in the demo in just a few minutes. Okay, what about when I'm interpreting the model, what if I want to know across all the factor ranges that I've studied? So varying silane across its range, varying sulfur across its range. In the whole study, the whole experiment, which factors are the most important to the response? So far in exploring the profiler, we've only looked at one moment at a time, one set of factor settings. But what about globally? What are the most important variables in this model? The answer for that is something available in that red triangle from the profiler called Assess Variable Importance. So here's an example with a different data set. This data set, so Assess Variable Importance becomes really important when you're not in the DOE setting. In the DOE setting, it's easier to understand this without needing a tool like this, but this tool becomes very helpful when you have observational data. So if I'm a medical researcher and I collect data on patients, like in this example, this is data about diabetes, and I know things about the patients like their age, their gender, their body mass index, their blood pressure, cholesterol, 2 parts of their cholesterol measurement, and so on. So I know biometric data about my patients. I can't design that experiment. I can't force someone to have a particular gender or a particular age. It's observational data that's just coming to me. In that kind of context, this Assess Variable Importance can be really valuable to see what, you weren't designing the experiment, but you're just getting the information, and now you're gonna find out what was really important and impactful in the model. So, in this case, we're just going red triangle again, Assess Variable Importance. Because this is an observational data, I want that third option of Assess Variable Importance. If it's a DOE, I want one of the higher ones. You can read more about this in the documentation. I can answer questions. But once we do the Assess Variable Importance, it shows us a ranking of these guys. It shows us just their main effect, but we've already seen when there's interactions involved, we don't just want their main effect. So it shows us their total effect, taking into account any ways they interact with other factors. And then it shows us how important they are. So a lot of this means a lot of importance. So in this model, gender is actually the biggest predictor of this diabetes disease status. Their body mass index is the next biggest predictor. So this is ranking for us the variable importance. This is based off of some simulations that are happening in the background. This is a complex model. This is a neural network model. But it doesn't matter that it's a complex model. JMP can do a simulation to figure out the answers when it can't just use the model to do it. So it doesn't matter your type of model. You can still use this variable importance. This just looks a lot more complicated because of the type of model it was. And then I colorized the plot to show this was the most important. Next most, next most. So I can reorder them, and I can also turn them this red color to help me see these were the most important. So this can be very helpful when you have many variables or a complex model. Okay, this is the only thing I'm going to show you that's not in standard JMP, but is in JMP Pro. There are so many great tools in JMP Pro, and because I work at JMP, I get to use JMP Pro all the time, and I really love it. I'm gonna keep most of my secrets. But this one I think is really nice. It's a nice feature in the profiler. If I wanted to know in my factor space where, and as I'm sliding around in the profiler, when have I clicked in a space that is not supported by the data at all? When am I extrapolating from the statistical model? That can be very hard to understand when you have many dimensions. It's easy with just a few. It's easy with a simple designed experiment, but it's very difficult when you've got a complex data set. So this tool called extrapolation control is really nice if you've got this type of scenario that's very complex. So here again is that neural network. It's the same one. I've put it onto 2 lines just so I can see it more instead of stretching it across, but it's the same. This is the diabetes disease progression response, and there's age, gender, BMI, etc. All of these are the factors involved. So it's just split onto 2 lines. So here I'm turning on extrapolation control. I'm turning it totally on. And now you see it's shortened these ranges, very much like when we had a part of the factor space that we weren't allowed to use. We had a linear constraint before. Now it's not a linear constraint, it's just a part of the factor space we never collected data in. So it shows us really easily, if we turn it totally on, it won't let us go over into that region. If we turn on the warning, we can go into that region, but it warns us, you might be in a part that's not supported by the data. So this can be great in a context where you've got something very complex, or you've got observational data, and you don't really know your factor space and where your data were collected. Okay, this one is another weird one. So this scenario is when you have a mixed model. So a mixed model is when you've got fixed effects, and all we've seen so far is fixed effects. I haven't shown you any mixed models yet. If all we have is fixed effects, but now we add in something random like the batch or the lot, something where there might be variability coming from it, but I'm not really controlling it, it's just happening. Maybe the operator, an effect of which operator does something. This is no longer one of my experimental factors. It's instead a factor about how I'm designing that's going to bring variability, but I can't really control it. So in that kind of situation, we call that a random effect. And now we're in what we call a mixed model. It's mixed with random and fixed effects. So when we're in this scenario where we have a random factor, we can still get the profiler just like we always do, but now what do we do about that random factor? It's actually a lot, statistically, there's a lot of complication about this. Now we can get something called the conditional predictions conditioned on a certain level of the random factor. So that sounds much harder than it is. It's just a red triangle click called conditional predictions that will only show up when you have a mixed model. So here's our mixed model. This is something about the measurement of cholesterol in patients. They were assigned, I think it was a crossover study, so they actually all show up in all of the treatment groups. They have measurements in April, May, and June. They have morning measurements and evening measurements. And the patient themselves is the random effect in this particular example. So the typical profiler just looks at the fixed effects and says, I'm averaging it over all the patients. They're like the experimental unit. But if that experimental unit is actually a random factor, you might want to say, well, patient 4 was weird. I want to see patient 4 in treatment A in April for the morning measurement. So these conditional predictions, I did not play that today. Just a red triangle option, conditional predictions, and now I have that random factor at the end. So now I can include that in fitting my model. So these conditional predictions are statistically a different calculation than the fixed effects predictions. Okay, this is another fun one. Yes?
Was that program also provided only for the pro version?
It should be the case that this will work for if you have a random effect in, when you fit it in fit model, there should be an option to assign a random attribute, and it should show up in the profiler when you have a random attribute assigned. I can confirm with you at the end, but it should be in standard jump. Okay, this is gonna be one of several ways that I show you that sometimes in an experiment, you wanna turn the dials on your factors and put them at specific factor settings, but it might be the case that you know you can't be that precise. Maybe you optimize an experiment, you find out you need to set your temperature at 42 degrees, but you know you can't get it exactly 42 degrees. There's gonna be some variability on how perfectly you can set those factor settings. Here is one way to deal with that. If you know that there's some variability on how precise you can be in your measurement of X, and you wanna see how that error propagates to Y, this is one tool that we can use. This will only work when we use in the column for the X variable, we use this column property called sigma. When we have that column property, this is a way that we can have the error in that X propagate to the Y. So this is a very silly example. I'm taking the area of a square as my response, and the side length is my factor. So I'm really just squaring, right? So that the error that will be calculated for the side length measurement will square to become the error in the whole area. So this is easy for us to understand, so it's not so hard for us to just do this ourselves, but JMP can do this for a much more complicated scenario also. So here we go, we've got the side length, we've got the area, and if I wanna assign that propagation of error, I use the red triangle, and I get that prop of error bars option. It only shows up because I have this column property. But then you can see when I have some amount of error, so if the sigma was 1, then this is the amount of error that's gonna propagate at that value of X into Y. This is one of many ways that we can take variability in X and push it into Y and see what happens. Simulations are probably a better way to do this, so we'll look at some of those options too. Okay, so we're at demo 2 of 3. Now we're gonna talk in the profiler about how to interpret the model. I'll go through some of these things with you and ask me if you've got questions. Why do I keep escaping this? I'm so used to doing this a certain way. Whoops. There it is, hidden. Okay, so we're gonna start again with the tire tread data, but I'm just gonna close this and start from another script. Let's use this one, so this multi-response. So if you open the tire tread data and you use that last script, it will open where it fit the model for the 4 responses and gave us a profiler for all 4 responses. Yeah, let's use this. Okay, so
Sorry. 그래서 지금 저희 타겟 트렌드 example 여시고 제일 아래 저 멀티 리스폰스라고 하는 그 쪽에 있는 초록색 버튼 누르시면 똑같은 화면 나와요.
yeah, thank you. I actually probably should have chosen just one. That's gonna get complicated, but that's fine. That's what we really work with, is complicated things. So we wanna talk about interactions. So let's start there. If we look at this overlaid interactions, this is gonna help us understand. It'll show us all those traces of potential ways the slope changes. So overlaid interactions. Now, instead of just seeing the one main line, I see its potential. But remember that that's potential is only 2-way interactions. So there might still be even more extreme things if I click around in the space. Like if I come over here and move this way, you can see that some of these traces are moving around. So it's not saying that's every trace it could possibly be anywhere in the space. It's saying two-way interactions. It gives you a sense of, will they vary? So here we can see that there's a little bit more of a dramatic change in the curvature. Here, this would be evidence of an interaction, something that's really steep, something that's really flat. But a lot of these actually don't look like there's an interaction. They look very similar, just maybe raised higher or lower. Another way to look at interactions from this red triangle that I did not show you is overlaid interactions. Let's look at the two-way overlaid interactions. Nope, that's what I am looking at. What's the other one? Interaction profiler, this one. Okay, overlaid interactions is what we just looked at. The interaction profiler is another way to get a sense about these interactions. So this is, again, thinking about pairwise. So let's look at maybe abrasion and this is, I think I might need so this is like the lowest possible curve and this is the highest possible curve for sulfur on abrasion based on the measurements of, is that right? Why are these the same numbers? That's worrying me. I think this model is not the model I was looking at before. But this is giving us essentially the extremes. So again, we're looking at two factors at a time, but it's telling us this is the one extreme of what this interaction could look like. This is the other extreme of what this interaction could look like. So between these two plots, there's two different ways to get a sense about how those two-way interactions are affecting. It is really hard to visualize more than two-way interactions. It gets very complicated. I think clicking and dragging in the profiler at that point is probably the easiest tool. Okay, and then we can also turn on the data points if that helps us also understand this model better. So another red triangle option was just data points. They get really big and bold when they're close to where you are in those crosshairs, and they get light and tiny when they're farther away from you. So as you move around in that space, you'll find different points lighting up as you understand how your model is close to those points. Okay, and then assess variable importance, that option right here. We use the dependent resampled inputs. This was the choice that I made when we had observational data. Let's use independent uniform inputs in this case with this designed experiment. That's a better choice here. And so it gives me the summary report. And let's look. So in this case, I can see them one by each of the four responses, but I also see overall for any response. So this is a very important thing. If I've designed an experiment that had 4 responses, I don't just want to know what's important for one response. I want to know for the entire set of responses. So for the entire set of responses, silica is the most important variable, then silane, and a bit below that, sulfur. Okay, I'm going to open up that diabetes data set also from the journal just by clicking on it. I'm going to run this neural script here in order to get this profiler. And here I first want to show you that extrapolation control. So most people will not be able to follow me. This is the only Jump Pro feature that I'm showing you. But extrapolation control, if I go to turn this on from the red triangle, it immediately shortens these regions. And I can see there was no data outside of this part of the region. If I were to turn the data on as well, the data points, the dark spots are the ones really close to where we are. So in some of these regions where we would be extrapolating outside of it, like here, so this line was very short, you can still see there is data. So there are patients in our data set that have a total cholesterol in this region, but they don't have total cholesterol in this region and the rest of these settings where they're at. So that's why it's extrapolation, because it's a very multidimensional space. And even though we do have patients with high cholesterol, we don't have patients with high cholesterol that also have average BMI, average age, and so on. So it helps us understand that. I'm going to turn the data points back off because there's so many that it's actually hard to see. So here with extrapolation control, it forces, I cannot go search around in the region that's extrapolation, or I can turn this to extrapolation control warning. And now it's just going to tell me that I might be in an area with no data support.
이거 참고로 프로 기능입니다. 네, 프로 기능이라 아마 쓰실 분들이 많으신 것 같고, 네.
Okay, one more thing to show you here, which is just that assess variable importance again. I'll choose the dependent option here for this observational data. Here it shows me what we saw before about which variables are the most important, and I can choose things like colorizing the profiler, so I can easily focus in on where the importance is.
May I ask you what is the difference between the assessed variable importance and log worth? I didn't know the variable importance, so I decided to which factors affect to something. I show the log worth value.
In many cases, they might be the same thing. Where did you get the log worth? What model were you using? In fit model? So the log worth will tell you, for the model that you've described, how important. The log worth is actually the log base 10 of the p-value. It's like how many decimal places were there until you got to a number in the p-value. So if you have a log worth of 1, that says it's not statistically significant. But if you have a log worth of 3, that's becoming very statistically significant. There's a good chance that those will tell you exactly the same story. The only time that they might differ is if your model was not very descriptive of what actually happens with your data. So when you set up a model, you have to know, do I want to put interactions in? Do I want to put quadratic effects in? How complex do I want to make this model? If you make your model too simple, then you might not find the same answer, because the method that this is using is like a bootstrap forest. It's much more able to find nuance even if you don't tell it what the nuance is. But in most cases, using the log worth will tell you a very similar story. Yes?
The variable importance will be the same as for predictors for you?
It should, I think it will be. I think it's being calculated the same way. We can investigate if you want to, but I'm pretty sure that that's going to be the same. Yeah. Okay, so we finished demo 2. We're now going to turn to optimization. Stop me before I move if there's anything else you wanted to look at with these.
더 보고 싶은 게 있다. 네, 나는 더 궁금한 게 있다. Okay, I think we are good.
Okay. Okay, so our last section, optimization. Very often when you are, especially if you're designing an experiment, this is often the goal. You're trying to get to this point. The rest of it was interesting, but this is what you really want. So back in our tire tread example, if our goal is to maximize abrasion, to maximize modulus, to match a target for elongation, we want to match the target value of 500, and we want to match a target for hardness of 67.5. If those are the goals of our experiment, then when we enter these goals, either from the DOE part, or we can enter the goals here, and I'll show you this in a second, the desirability functions will pop up, because once we've told it what we're trying to do, then JMP understands, oh, this is what you desire. So it comes up with this desirability once it knows what we're looking for. So the desirability functions are trying to say, so this is 0 and this is 1. A desirability of 1 is yes, totally desirable. A desirability of 0 is not desirable at all. So anything on this side is good. So this point, we look across, that's when hardness is 67.5. So this function is saying, you told me that you want hardness to hit this target of 67.5. So when it's at 67.5, I JMP believe that that's 100% perfect. We did great. The desirability is 100% exactly at that value. How steeply should it decline away from that? do I say 0, all the way up to the number 67.5 and now it's 1? That would be a terrible problem to optimize. We want a smooth relationship in this desirability, but how tight you are here is a choice that you need to make that JMP will respect, and it will give you slightly different answers depending on how you set this. Sometimes you'll want to tell it a spec limits, that it could be 67.5 plus or minus 2. So there are several ways that we can tell JMP to be more specific than just this is the target. We want to tell it how important it is to get very close to that target. What is close enough to have a high desirability? So you can click and drag these guys in if you want this to be really tight, or you can drag them farther away if you don't actually need it to be perfect, or you can add spec limits. So same thing here, this guy that is desirability of 1 when we're at 500, because that's the goal we told it, and then JMP is giving us, I didn't set spec limits yet, so it's just giving us something to start with for how steeply to achieve that. For maximize, it's saying when you're at the maximum of both modulus and abrasion, it's 1. When you're at the minimum, it's 0. And there's some kind of a relationship to get between the 0 and the 1. So you can adjust anywhere there's a little thing like this. You can click it and drag it and adjust to make that more or less steep. Less steep is easier as a mathematical calculation, and it's more stable. But you also don't want it to be non-informative. So JMP is trying to hit a balance until you tell it more information. Okay, so what I have done here is in the platform, we'll choose the button and we'll click to maximize the desirability or optimize. When I do that, right now it's still at its middle settings, 1.2, 50, and 2.3. In a second, it's going to adjust. So now it really dramatically moved sulfur. It moved silane up a little bit. It moved silica up a little bit. So this is the optimum. How does it balance the 4 responses? That's something where you get to tell it how important those responses are. If you say that the importance is equal for all of them, then it will equally mathematically weight those 4 desirability functions. If you say that actually the hardness is really important and the others are less important, you have to decide how much is really important. You're going to put numbers in that JMP will have add up to 1 and then will proportion. So you could say importance 1, 2, 3, and 4. But what that means to JMP is there's 1 component for abrasion, 2 components for modulus, 3 for elongation, and 4 for hardness. So 4 plus 3 is 7, plus 2 is 9, plus 1 is 10. So that means this is 1/10 of the importance. This is 2/10 of the importance, 3/10, and 4/10. So when you write that importance, it's not a ranking. It's a how much out of a pot should go to this. And then JMP is going to put that as a multiplier, a weight in that desirability function. So if we want to do this optimization, we're going to go to the prediction profiler. We're going to choose optimization and desirability. We get a control panel, and then we'll click the maximize desirability button in order to actually accomplish this. I'm going to just skip the videos and just show you this in the demo. If we wanted to explore the distribution of the model outputs as a function of random variation. So I told you before, there's several ways in JMP to take variation in the x's and propagate it to the y's. Simulate is going to be the feature we want to use for this. So in a moment, we'll do this demo. We'll look at how to optimize. We'll look at how to simulate and put noise on the factors. We can also put noise on the response if we want to. So I'm not going to show you any of these videos. We'll just do it in the demo. When you are simulating, if you have spec limits on your response, you can also calculate the defect rate. How often do you not achieve your spec? So as long as we've got spec limits, we'll add some spec limits. We can use that simulate to explore our defect rate that we expect based on adding noise in the factors, potentially noise in the responses. What about when we see that defect rate, JMP could actually give us tips about how to improve that defect rate. So there's another feature we'll look at called defect profiler and defect parametric profiler that are actually going to tell us recommendations for how to improve the process in order to have a lower defect rate. And I'll show you that here really quickly. So when we go to simulate, we're going to fill out this. So this is our silica, silane, and sulfur. And we're going to expand this. First it tells us it's fixed when we're simulating. We're going to ask it to be random. We're going to choose a distribution. I'll choose normal for all of them, but there's like 16 different distributions you can choose. Then the parameters for that distribution. So we'll update for the random noise we want to happen in the factors. We can also add random noise for the responses if we want to, and we definitely want to put spec limits for the responses. When we put spec limits for the responses, they show up as these dotted lines for each response. And that helps us see, when we click the simulate button, it helps us see the distribution and how much is falling out of spec. Then it calculates that defect rate for our 4 responses and gives us a summary defect rate for the whole set of 4 responses. So when we are simulating, we can see the defect rate if we add spec limits. Then we can ask for this defect profiler and the defect parametric profiler. And this is, we're trying to get to the bottom, low defect rate. 0 is down here, 100% defects is up here, so we want to be low. Right now we are at the red dotted line. So if we look at the red dotted line, how could we be lower on one of these 4 colors? For silica, we could be lower if we followed the red to the left. So from the spot we're at, if we followed this red line down, we could get lower. What does that red line mean? It says shift the silica mean that way. So right now I have the simulation saying that the silica mean is 1.2. JMP is saying, can you get that lower? Go back to your process. See if you can get that lower. If you can, I think you can get that you'll meet your spec better for your responses. So if we lower that, so here was our overall defect rate is 2% before I make that change. Now we lower it to 1, so I dropped it from 1.2 to 1. I hit that simulate button, and now my defect rate is 0.3%. I dropped from 2% to 0.3%. Now, that doesn't mean I can actually achieve this. I need to know that I can make that shift change in reality. This is a simulation. This is telling me what will happen if I can find a way to drop that mean. Okay, so let's look at those things really quickly. I did it again. Here we go. So if I go back to the tire tread data, I just opened another version of it, and I open that the last option, the multiple response. If I go to the red triangle, optimization and desirability, here's where this control panel is. That control panel lets me adjust the targets or the importance for the desirability, which I had already set up. So these are all, it's saying they're all equally important. It's saying I want to maximize abrasion and modulus. I want to match a target, and here's the 2 values I want to match for the other 2 variables. So that's set up just like I want it. For the factors, it shows if I have any linear constraints, they would show here. And then I can just click maximize desirability. So when I click maximize desirability, it does its best. If we tightened this, we might find a different optimum. So you can play around with how precise you need to be if you don't yet know, or you can add spec limits if that's something that you have as an option. So if we go back to the prediction profiler red triangle and we choose the simulator, so optimization is quite simple once you've got it set up. You just hit that button. The simulator now gives us a chance to explore what-if scenarios. So here's where I might decide to make silica random, silane random, sulfur random. I'm going to make these means 1.2 is where I started before, and I had a standard deviation of 0.1. And this one is 50 and 2. And this one is 2.25 and 0.15. If you're trying to follow along, you could put any number there right now just for the sake of the simulation. And then for the responses, here's where I could add noise if I wanted to for the response. That's not what I'm doing in the simulation, but you actually can add noise on the response as well. But from the simulator, I can choose spec limits. And here's where I can say, for example, if I want the abrasion to be with a lower spec limit of 110, modulus and upper spec limit of 2000, and elongation to be between 350 and 550. And notice I did not make that centered around 500. So I'm allowing it to roll more toward one side than the other. And then for hardness, 66 to 74. If that's the settings I want, now I come way up here and push that simulate button. Simulate button, now I see my defect rate. If I now want to do some exploration of how I could improve it, from the simulator, I choose defect profiler. I didn't really talk through this one because I like the parametric so much better, but now that I've put the profiler on, I can ask for defect parametric profiler. Here's where we learned to get as low as possible from the red dotted line where we cross any of these. Like I could have moved on the green one a little bit, but my most dramatic effect was this red line on silane dropping that way. The red line says do a mean shift. So now if I take that information and I come back up here and I change the mean of silica to 1, I drop it from 1.2 to 1, and I re-simulate. Right now, I'm at 0.02. It's random, so you'll have something similar but not the same. I click simulate, and now I've dropped that defect rate to 0.3. Okay, we are out of time, but there's so much about the profiler that's awesome. So if you did not yet download the materials, jump.com/discovery workshops will give you the step-by-step demos that I covered. At the end of that document, there is a list of every question I posed. The engineer wants to do this, what's the solution? And the page in the document that describes that. So I hope you'll use that and explore it. Herbert and I can answer any questions at any time, and do be in touch with us if there's anything we can help you with.